Alright, so we're going to look at one type of narrowbanding, and this type of narrowbanding will be called shunt compensation. Alright, so we're going to treat the first stage of our, so let's look at our two-stage op amp first. We'll draw the two-stage op amp with an NMOS input and a PMOS current mirror load. Alright, so here's our two-stage op amp, and what we're going to say, we're going to treat this first stage like it's just a GM stage. Now, why can we treat this stage like it's just a GM? Well, it's not really just a GM, but when we make Thevenin equivalent circuits, we can treat nodes that are high impedance like they're current sources. So this node is definitely a high impedance node. It sees the output resistance of transistor M4 and M2 here. So what we're going to say is that we can model this first stage like it's just a GM. In other words, we can put an input voltage here, and we can make it differential, I suppose. So let's do something like this. And then we go into our second stage, which is composed of transistor M5 here. So we can say that this has a voltage gain that's equal to minus A2. So we'll call this GM1 and minus A2. Now if we were to look at this in the context of the entire op amp, we could say that this whole thing was the entire op amp. Our output still comes out of A2. This would be our non-inverting terminal, and this would be our inverting terminal for the op amp. Okay, so we're treating this first stage like it's just a GM, and we're treating the second stage like it's just a voltage gain. Now, what we want to do is increase a pole that's so dominant that it dominates the two poles associated with just this node, the output node here, so node 1 and node 2. Normally we would have some parasitic capacitance at this node and some parasitic capacitance at this node. And what we're going to try and do is add a capacitor at this internal node that's very large. So we'll call this CC. So what we're doing is adding a capacitor at this node called CC. Now if you were given an uncompensated op amp, sometimes they might put a pin at this node so that you can add that compensation capacitance externally. Alright, so let's put a test voltage source that we'll call VI into our non-inverting input to our op amp and measure the change in voltage at the output. So if we put this test voltage in here, we would get a voltage Vx at this node and a current Ix that flows through the capacitor. So we could say that Ix was equal to minus Gm times Vi. We know that Vout is equal to minus A2 times Vx. And we know that Vx is equal to minus Gm times Vi times the impedance of the capacitor, 1 over SCC. If we calculate a voltage gain from all of these terms, Vout over Vn with respect to frequency is equal to minus Gm1 times A2 divided by SCC. Now what we're going to say is that we want the closed loop gain to intersect this curve at the unity loop gain, the unity loop gain, in order to have a phase margin of 45 degrees. So if we plot the transfer function here, we would see something like this. Now this transfer function is only valid at high frequency. This is not what the actual transfer function of the circuit looked like. This is with our simplification that we're looking at. But we're trying to find out what the higher frequency response of this circuit is. So here we have a one-pole roll-off that starts infinity. So remember, transfer function is not valid here. It's only valid in this high frequency region. All right. So for a 45-degree phase margin, we want the magnitude of our transfer function, VO over VI, at the frequency of the unity loop, where the unity loop gain occurs. So we'll call that frequency omega unity loop gain, is equal to our DC closed loop gain, and we want it to equal GM1 over omega unity loop gain times CC. Sorry, I left a term out here. There should be an A2 here. Just taking this equation from the prior page of notes. Now, if we solve for the compensation capacitance value, we'd find CC is equal to GM1 times A2. We want the unity loop gain to occur at the second pole in the circuit, so times omega 2 times CC. Or sorry, A0, our closed loop gain. And if we met this condition, we'd have a 45-degree phase margin. Okay, so we will look at one more example before we move on to our two-stage example, or two-stage compensation, using pulse splitting.